All right, it's time. Welcome back to the lecture of Introduction to Computer Network. This is week 4, episode 8. Yep, okay, live chat is working. So let's go ahead and walk through the topics just a little bit more. And the first part of the lecture today is going to be slightly shorter than 50 minutes. The first part is going to be about HTTP messages again, but this time on the HTTP response message. And then we'll do the quiz number 8. We'll be spending some 3 minutes there and then move on to the other topics related to HTTP as well. That first is the cookies and then web caching. There are 2 forms of caching. One is the local cache, the other is the proxy server cache. So we'll hear about these more, and let's go ahead and start. Now, finally, the HTTP response message. Okay, the second type of messages defined in the HTTP protocol. You see here, generally, 3 parts. First, the status line. Second, the header lines. And the third, the data. So the entity body, so to speak, from here and down. Okay, and these are very similar to the header lines we see in request message. Each line, you see attribute and the value. Attribute and the value. Status line. 1, 2, 3. Again, 3 components. Let's go through each one of them as well in a bit more detail. In status line, first here, familiar. So the version of HTTP the server is implementing is the first component in the status line. Second, this is the status code. Okay. So in HTTP, it defines quite a number of these status codes. Each of these indicate a different condition. Some more related to the server, some more related to the object being requested. And for each of these status code, there's a status word being shown as well. That's the third component in the status line. So 200 here indicates okay, meaning the HTTP server is working well and the object you're looking for has been found, and it's going to come here in the body entity. Now, second part, the header lines, we see date. Yep, this is the date, time, the request is being filled, and this response is being generated. The server, this is an Apache server, version 2.0.52. Yep, Apache is one of the most commonly used web server implementation. I think you heard about the other one, Nginx. So Nginx is certainly rising. Okay, it's not quite yet the most popular one. Well, let me clarify. By popularity, I meant the number of machines running a specific version of web servers. So Apache is still the most used web server. But if you count only the number of downloads recently, it might be Nginx. That's why you see I said that it's actually rising. So I think maybe in just a couple months there will be more Nginx server than Apache servers. Last modified, so this is to indicate when is the object you're downloading last modified. Oh, okay, it's really long time ago. All right, ep8. What is this? This is actually, for each version, of the object that you are downloading, there comes also with a version number. So ep8 there is to indicate the version number. Nowadays, as you see, the HTTP protocol is not used only for downloading purpose. It can also be used for uploading. if there are multiple users there using different web browsers trying to upload the file, for example, Poly and Caleb, the TA, tries to upload and override the grades Excel file, then you might have a consistency problem there. So the number here is to break tie, to make sure that a newer version does not override an older version or something like that, to resolve conflicts, so to speak. And accept range. Yeah, yep. So, you know what? Earlier when I mentioned the head comment in the HTTP request message, right? So when you send such a comment in the HTTP request message, the server responds with only the status line with the header lines, but without the data. Okay, so server there can actually tell the client, you know what, I'm a server that allows you to request content in terms of bytes. So the client there seeing this can then send the request more officially, instead of using the head command, using the real get command, and request to download byte 0 to maybe 1023 or byte 0 to byte 100. Okay, so you could do a range request in a way. And the server's next header line, content length. This is to indicate the size of the file or the size of the object that you're downloading. So you see the file size of the object is one critical parameter. Okay? If you're implementing a web server, you need to know a way to find out what the file size is or the object size is. Okay, so size is a bit messy. Let me clear the markups. Keep alive. Oh, good. This web server implements persistent connection. Okay, and so it indicates timeout interval is 10 and maximum 10 requests. So this is a persistent connection, but in the connection, it only accepts up to 100 requests. All right, so if it's more than 100, then you will force close. The server will force close the connection. So connection, keep alive. Content type, yeah, just like the client size header line we see. Yeah, the client accepts content of a certain format. Here, okay, this is to indicate the object the client is asking for, which format it is. And we see this is text-based HTML file and it's coded in ISO AA59. Right? And empty line, indicating this is the end of the header lines. Right after the empty line, the data goes here. If it's an HTML file, then hey, text starting from here. Okay, the first file. So this is an example of HTTP response message. You see the structure is very much like the HTTP request messages. Next is just to share a bit more. HTTP response messages status code. We've seen earlier in the example 200 OK. This is saying request is successful, object is already embedded. 301, that means the server is saying the object is moved to a new location specified later in this message. So sometimes when you run into a message like this, you see, oh, click here. That's going to take you somewhere else. It's a redirecting link. If you see status code 400, that means your HTTP request format is not quite correct. Bad request. 404, that means the object you are asking for is not found. 505, HTTP version not supported. So in case you're using a very old browser, or if you are contacting a server that's very, very old, and yet your browser is implementing something newer, then you might not be able to communicate. The server is going to tell you this. Sorry, 505. Good. And now we're ready to look at an example of what HTTP requests and response might look like in real life and in action. So what I will show you in the demo coming next is to do this. Telnet to the favorite web server here, and we're going to use this machine here that the textbook author has set up for us. So we'll telnet to gaia.cs.umass.edu at port 80. Okay, what it does is to open the TCP connection to port 80 where there's a server already running, a web server already running. And anything typed in will be sent to port 80 at this guy. Okay. So Telnet is a remote logging application, just like SSH or RSH, if you know what it is. It's another remote logging command for native Unix users. Alright, so Telnet is very, very old. Many operating systems probably doesn't support it anymore. But I've already installed it on my Mac, so we're going to show that in a little bit. Now, once we Telnet to the web server, and we'll type up some things. Okay. Let's try typing this. Get path name and file name as the argument for the get command, and then the version of the web browser. So we'll be pretending that the Telnet here is a HTTP 1.1 client. And host gaia.cs.umass.edu. Right? So header line. So essentially we are trying to do a human web browser. Okay, by typing online right here an HTTP request message. So once we are done with this, we hit return. Okay, and then we hit return again. Needs to have a what? A \r\n here in order to complete the HTTP request. All right, so the whole thing is going to be like this. And yeah, we'll see what pops up in return, what the server there at umass.edu sends back. Okay, let's not sniff the traffic. Let's just look at the response coming out of the Telnet program. All right, so let's switch to the demo mode. All right, let's Telnet to gaia.cs.umass.edu at port 80. All right, connect it to gaia.cs.umass.edu. Now let's pretend to be a web browser. Get. Oh, wow, that's pretty long. The path in the file, pretty long. Let's copy it from the slides. And over here and print. All right. And then host poly.ntu.edu. How about that? All right. And one more empty line to indicate this is the end of the header lines. There we go. Wow, it's returning a lot of things. Scroll back, and scroll back. Wow, very long in fact. But it looks like it's an HTML file, right? It's an HTML file. Now, this is a hyperlink to an text HTML file. Okay, let me scroll a bit faster. I don't know how long this is. Oh, there we are. Yeah, so we typed up this line here. Okay, and we also say we are host poly.ntu.edu.tw and an empty line, and then return again. The whole message gets out to the web server at gaia.cs.umass.edu, and the web server returns this http://11 to the 200. Okay, and header lines number 1, the date. Header line number 2, the server. Oh, it's an Apache server. And X power by PHP. I see. Content length, content types, and hey, empty line to indicate this is the end of the header lines. And starting from here, the real body. Okay. So we get the output of calling this PHP query at this path. Let's see. Interactive problems, computer networking, a top-down approach. Oh, okay. So this looks like the main page of all these interactive exercises that we see every now and then on the slides. All right. So there, essentially very text-based interaction between the client and the server. As human beings, we could also do it right here, right now, online, as a web browser. All right, good. And I think, let me just go back a little bit here. You see here, 200 is a very classic example of, hey, the syntax defined in an application layer protocol. In HTTP, to be exact, 200 is to indicate OK. So OK here is just to say it explicitly, the semantic of 200. Right? So that concludes the messages format, semantics and syntax of HTTP. Good. And that takes us as well to quiz number 8. It's actually very similar to quiz number 7, but what I'm showing here is an HTTP response message or HTTP reply message. Okay, read through it and tell me. Q1 is asking, was the code found successfully? Was the document found successfully? Q2, how many bytes are there in the document? Q3, what are the first 5 characters of the document being returned? All right, look it up and tell me. You have 3 minutes of time. Hey Siri, set a timer for 3 minutes.
Your timer is set for 3 minutes.
All right, so if you discover the answer to Q1, Q2, Q3, just type up. All right, time's up. So we do receive, a few teams typing up their answers. I think team there, Bian Jun Tian there is team number 14. So 14 says yes, and the size being 3A74 bytes. Very good. Look at the content length headline. Team 1, Team 12, and Team 5, you guys are doing great. Great, so now you see HTTP response formats. It's very readable. You just need to do a bit of guessing and maybe look up on the web from the documentation. All right, and let me also address a couple questions from the previous section of the video. So we were talking about HTTP messages, the response message. There are a couple questions. One is from Rocket asking why Nginx versus Apache. Why Nginx is becoming popular these days. Yeah, well, the basic implementation of two web servers are very similar. Nginx is just slightly better in terms of performance. But Nginx also implement these additional support so that if you want to build a server cluster as your startup company is growing, one physical machine to support the service might not be sufficient. So if you want to grow your server to a server farm, to a server cluster, then Nginx has got all these nice tools, nice softwares allowing you to balance the load across the physical machines. Really cool. But, by the way, the load balancing part, those additional software, then will not be free. Okay, so nice business model there. Get you hooked, and then they charge you. All right, so that was Nginx versus Apache. Tim there was saying that, okay, so you use Telnet to log into PTT. All right, for international students, you probably don't know what PTT is. PTT is pretty much like the Reddit for Taiwanese students. Well, I'm not sure. The students probably are not going to the PTT, but the 30-something and some 40-somethings like to go to PTT. A team there, not saying that you are a bit older than the other students. I'm just, saying that it was popular for students who are now reading the 30s. It was super popular then. Let me put it that way. All right. So that was HTTP messages, the end of it. And we move to the next topic, the cookies. Next, cookies. Yeah. Many websites these days would try to prompt you to set up cookies before they allow you to visit the website further. So it's very, very relevant to our everyday life. Let's see how it works. Okay. First thing is, the cookie setup process is always initiated from the website. So meaning from the web server that your web browser is requesting objects from. So web server there is going to send a message to the web browser carrying a special header line. Okay, it's the cookie setup special line. And the web browser there, upon receiving such a message, it's going to generate a corresponding message if you click OK to insert cookie. And that message is going to carry again a special header line saying cookie OK. All right, so exchange of messages between cookie setter and cookie allower. Now, when you say, okay, I will allow setting of the cookie, your browser is going to add an entry to the special cookie file on your local disk. Okay. So that is exactly what's expressed here in the special cookie setup line. And when the server receives the message allowing cookies, server would then add a special entry as well to the backend database. And that entry set up here and here will actually map to each other, allowing the server to identify who you are and when have you visited the website last time. Okay. Let's use an example to explain. It will work slightly better. Let's say Susan always accesses internet from her PC. And she's visiting a specific e-commerce site the first time. In the initial HTTP request, that arriving at the server, the site will then create a unique ID, okay, and that will be an entry being added to the backend database. All right, so that ID is going to be carried. Okay, in the message, the site sends back to Susan. So that's going to be set cookie and then the number created here. All right. So local hard disk you have there, or Susan has there, will have that entry, okay, set up in the cookie file. So this will go back to the server, okay, carrying also that special ID that Susan has already allowed to set up. And then at this point in time, the server would finally enter the entry to the backend database. So that's the way it works. Let me illustrate, okay, and so that you know clearly what's going on. Client, server, or Susan, Amazon.com. Okay. Now, at the client side, you have this special cookie file, and it's managed by the web browser. And you might have clicked OK to eBay. So eBay has already set up a cookie entry carrying unique ID 8734. Server here has a local disk as well. It's maintained more as a backend database instead of just a simple file. Right? So, but when you visit the website Amazon.com the first time, you send an HTTP request message. Now, of course, you have not yet been in Amazon before, so there's no entry for the Amazon website. Okay, so in your initial HTTP request message, there's not going to be any cookie special header lines. All right. So when Amazon.com here receives HTTP request, of course, it will try to grab the objects that you're looking for and try to generate the HTTP response with it. But in the meantime, it will be creating an ID, okay, for this particular user, okay, and add that to the database. And in the response, it carries the web object that you're looking for, but it also carries the special header line, the set cookie line. Okay, and hey, see the ID created is carried over through the HTTP response message back to the user. So, web browser here sets up one extra entry saying, hey, for Amazon, the website, use ID 1678. So for the subsequent visit, subsequent browsing, all the HTTP request messages is going to carry the cookie OK and I am a user 167A header line, right? So here the server, of course, will be generating the web objects, generating the HTTP response message that you're requesting with the request message. So response message. But the response message might also contain additional content, okay? Server there could be seeing your browsing history a couple clicks back and discover that, hey, you might be looking for a specific item, okay? And then recommend potentially items you'll be interested, okay? So that might also be part of the response messages. So showing the items you are looking into buying as well as related products. Okay, so for example, if you are looking to purchase a phone, then the website might be recommending a phone case, okay, or a number of phone cases. So what's amazing there is 1 week later, okay, when you come back and try to purchase something from Amazon again, okay, the first request message you'll be sending will already be carrying the cookie entry. Okay, so once you have it set up locally on your cache file, or on your cookie file, for all the subsequent HTTP requests, it's going to by default carrying the cookies. Amazon here will know, yeah. So over time, the server will know, probably your profession, probably your income level, things like that. Okay, so that's why it gives people a certain creep about setting up cookies, and you might be warned, be careful about setting up cookies there. Now let's discuss cookies a bit more. We're going to talk about the trade-offs of using cookies. First, the cookies from a business perspective, from a website's perspective, is actually quite convenient. So you see, you can authorize the users quite easily, okay, by looking at the ID in the cookie header line. Tracking the shopping carts as long as the ID is the same, right? This is items purchased from the same user. You can recommend items so that the users will go, wow, cool, that is exactly what I was looking for next, right? If the user is purchasing a phone and the website suggests purchasing of a phone case. Yeah, and browsing emails, yeah, you will not want to try to log in and type up password again and again. You want to be able to maintain that email reading session, email sending session over time and log in just once. How? Very nicely through the cookie line in the HTTP request. Okay, quite convenient. Okay, otherwise, you guys, including Polly, when I read my Gmail, I have to log in again and again and again. There's no way we could live like that, right? So, convenience. But on the downside, those websites would be able to learn a lot about you. Okay? So you store emails, that's pretty much your personal life. You store your purchases there, that's pretty much also your personal life. Okay? So over a long time, you can imagine Google, Amazon, Facebook, all these major websites, they know a hell lot about you. That's why people are freaked out so much about these big sites, okay? Allowing them to set up cookies, allowing them to store information about you, okay? So, downside, privacy, okay? Now, another perspective is more technical, keeping states. Now you see, hey, there's ID on the local cookie file. There's ID stored at the server side, the backend database. So, server and clients are now storing states of each other, about each other. But some of you might go, hey, wait a minute. Didn't we talk about HTTP being a stateless protocol? And what's nice about stateless protocol is that, hey, none of the endpoints need to store anything about each other. Okay? No storage requirement. And you don't have this problem where, hey, if the connection between the client and server is broken, and you might have these inconsistencies in the states they maintain for each other, right? You have to reconcile and resolve conflicts. And that is actually a very, very hard problem, okay? Who do you trust more, the server or the client? Okay, sometimes it's a bit hard to say, okay? So cookies here you're seeing is, in a way, a hacking HTTP such that we can maintain states, because HTTP was not designed at the first place to maintain states. But then now with the cookies, we have this issue potentially between the client's cookie file and the server's backend database. What if, the entry is inconsistent? Then you might have an issue as well. So trade-off in terms of usage, okay, in terms of privacy concern. Trade-off in terms of technical difficulties maintaining the states. All right. All right, so that was cookies. Good, no questions asked. So let's go straight to caching. So this is the second thing we want to spend quite a bit of time about. So we're going to cut short in the middle of caching and then take a break and then resume in the next session, the rest of caching. The next two topics are more about trying to reduce traffic between the server and the client, or trying to reduce the delay downloading a certain object. It's called the caching. Okay. So what cache means is to store a temporary copy of certain data. Okay. So conditional get here is like to have a local cache of the web pages that we have downloaded previously. Okay. So the goal is to not send the object again and again and again if the copy we're storing here is already the latest. Okay. Because as a result, we don't need to send the object, and that reduces the delay, and we also reduce the bandwidth requirement. Okay. And so saving the bandwidth is going to be good for everybody. So the way it works is this. Okay. So the first time the client downloads the web page, it's going to keep the copy of the web page on a local cache. So that's somewhere in your local disk. And in the meantime, we record the date, okay, the cache copy is downloaded. And so that when we send a request for the same page again, we carry this special line in the header field, the if modify since, and then the date, okay, of the cache copy, the day we have requested the copy the first time. And then at the receiver side, at the server side, the response will contain the no object if the cache copy is actually the most up-to-date, meaning if the copy at the server has not been changed after the date, then there's really no need to send it again back to the client, okay, because the copy right here is already the latest. So in that case, a special HTTP response message is going to be sent, and the status line is going to read like this. Yeah, 304 not modified. And in the body of the HTTP response message, it's going to be empty. Okay, so no need to send the object. And the way it works is more like this. Let me illustrate. The second time, the client here requesting for the web object sends request message and having this in the header line. If modify since the date the page was downloaded the previous time. And if the server finds that no, it's not yet modified, then send back a short HTTP response carrying the status line. And that's all. No data here. But otherwise, if the object is modified, then we send back a regular HTTP response that says 200 OK in the status line and the web object, the web page again, okay, in the body and the T. Web caches. The purpose is very much like the local caches, but the way it works is somewhat different, but not much different though. Okay. The main difference is this. In local caching, we keep a copy of the object here. Okay. But now we keep a copy of the object here in the web cache, or also known as the proxy server. Web cache or proxy server. Okay. And in conditional get, we still need to send HTTP requests to the original server. It's just that the original server decides whether to send the object with it or not in the response. Okay, sometimes yes, sometimes no. So we save a little bit delay and bandwidth this way. But in web caches, the goal is actually trying to satisfy some client requests such that there's no involvement of the original server required. Okay, so some of the clients doesn't need to reach the original server to get the object. And this is done by keeping a copy of the objects somewhere in the middle at the proxy server. Okay, so the way it works is this. Users will set the browser such that for all web access, let's go through the web cache. So subsequently, the browsers will send all HTTP requests to the web cache. So send it to the web cache. If the object, the page we're looking for, is already in the cache, proxy server sends the object back. So you see, it works somewhat like a server, but it's not the original server. It's somewhat a delegate of the original server having a copy here. Okay, so object in the cache, cache return objects. Otherwise, the cashier, the web cashier, would request from the server a copy of the object. So this request will be like, the proxy server here behaving like a client, of the original server. Web cache there, request object from the original server like a client. Okay. And after the object is downloaded here, the proxy server then sends the object back to the requester. So let me illustrate. If the object is not here, request go to the original server, response comes back, store a copy, and then forward it back to the client. And what's nice about this is, look at this client down below. If the client is requesting the same object, it's a hit here at the cache. Server here sends back the object directly without going through this segment of the internet. So, cache there acts both like a client and a server. As a server, so that it served the original client, the objects. As a server, because if there's a miss, it will be requesting the original server for a copy of the object. Right? So, some of you might see already, right? A web cache like that is actually preferred by the ISPs, which serves a whole bunch of customers locally. Usually people sitting close to each other tend to prefer fetching or tend to fetch similar content. So a lot of times ISPs might encourage you to set a web cache on your browser. Now let's go through a few examples to detail why using web caching. Local cache, nice, reduce delay, reduce bandwidth. Through this set of example, let me take you through what is the benefit of doing web caching. In a nutshell, a lot more delay and a lot more bandwidth saving. Good. The example. Setting is this. Servers up here, client down here. So they're part of the institutional network here. And the servers are connected to the public internet. And the internet connects to the institutional network through an access link. Let's assume that the clients here are browsing the web, requesting objects down from the server. The average object size being 100 kilobits, and the average request rate being 15 objects per second. Then multiply the two, you get the average bit rate, coming down this way, right? And that is 1.5 megabits per second. Now, let's see. Round-trip delay from the institutional router to any of the origin servers and back. That's set at to 2 seconds. And the link, access links rate, 1.54 megabits per second. And the local area network link rate, 1 megabits per second. Now with these, we will be able to calculate the local area network's utilization. 1.5 meg divided by 1 gig, that's 0.15%. But here, 1.5 meg divided by 1.54 meg, that's very close to 99%. And that is a problem if you recall. There's this component called queuing delay in the internet nodal delay. For transmission over a hub, there are 4 components: processing delay, queuing delay, transmission delay, and propagation delay. And the queuing delay is very sensitive to the utilization on the link here. Right? So let me take you here. Queuing delay. Just in case you kind of forget about it. It's very case dependent, and the determining factor is the utilization, which we call back then when we were talking about internet delay, the traffic intensity. So this is the amount of input, and this is the output capacity. You see, utilization again. When this is very small, queuing delay also very small. So as it approaches 1, delay becomes large. When it exceeds 1, delay is actually approaching infinity up here. All right. So close to 1, close to 100% delay, just very long. Okay. Let's come back here. Therefore, if we want to calculate the total delay of web request and object download, it will be round-trip delay here, plus round-trip delay here, plus round-trip delay here. 3 components: internet delay, access delay, and LAN delay. Internet delay, we already defined it. Just make it simple. Just say that it's only 2 seconds. But hey, here, fully utilized link with high queuing delay, it's going to be very long. Let's just say that it takes minutes. It could be even higher. And the LAN access delay. Now this is very low because utilization is super low. So let's say microseconds. Right? So 3 components. Which one dominates? Yep, queuing delay on the access link dominates. So bottleneck where? Here. In terms of delay performance. How do we fix this? Let's look at the second scenario. In scenario 2, let's try to address the issue here because this is the bottleneck link where the delay came from mostly. And let's blow it up 100 times. How about that? So using a fatter access link there. The result is that the access link utilization is also reduced 100 times. Less than 1% utilization, you can imagine the queuing delay being very, very short. That brings this component of the delay down to milliseconds. Now, why millisecond? If you recall trace route testings that we did earlier in chapter 1, right? What was that? Quiz 3 or quiz 4, isn't it? Yeah, most of the delay we see between 2 routers are what? 10. So 2 seconds, milliseconds, microseconds. Which of these 3 components dominates? Obviously, 2. And from scenario 1, we have minutes of delay to scenario 2. We effectively bring down the total delay. All right, great. Is there any catch? If you think about it, hey, bringing the access link capacity up 100%, that is actually not cheap. So increasing access link speed, no, not cheap. You need to purchase the new cables, of course, but you might also need to do groundwork. Okay, remove the old cables, install new ones. Just think about the labor cost there. And in addition to that, you might need to upgrade the routers there connecting the high-speed link, just so that you can accommodate potential traffic volume. So, yeah, very costly. Now in scenario 3, let's see if we could introduce something else instead of blowing up the capacity in the bottleneck link. All right, so that is for the first session today. We do have one more question. It's from Kevin asking whether the proxy server, so this is related to the web proxy, whether the proxy server can request objects ahead of time from the origin server. Well, you know what? I'm not aware of any proxy server implementing such a special mechanism, but I can see that if there's a flash crowd event where people is gonna log out and then try to check things out, then such a prefetching strategy will be a good thing to have, because that way you cut all these traffics going to the origin server and it serves with a much shorter delay, right? And it's a good time to take the break. We'll come back in 10 minutes. And let me apologize ahead of time. The second session is going to be slightly longer than the 50 minutes we are allocated for the lecture. So bear with me just this time. All right, good. So let's take a break. Hey Siri, set a timer for 10 minutes.
Okay, 10 minutes.
Yeah, if you're still watching, I'm just gonna stop the stream a little bit and then reboot OBS and come back because I am not very comfortable about having OBS running for full 2 hours. So let me stop the stream. I'm gonna restart OBS. So YouTube live session is gonna still be on. So, yep, stop. All right, good. We're back. All right, it's time to resume the lecture. Good, so the second session here, the topics are going to be first, to continue talking about why caching. So there is scenario 3 that's coming up. And then we'll talk about another application layer protocol, FTP. So to just give you a bit of idea how a very old protocol such as FTP is designed versus HTTP. And later on you'll see even newer application layer protocol, how they're designed. And then the rest of the lecture time is going to be dedicated to go over PA4, the video walkthroughs. PA4 is slightly tricky in terms of testing it. So try to see if you can follow PA4, the part 2 a little bit closer. All right. So that's my alarm sounding. Good. Perfect timing. Let's go ahead and start. Try to wrap up caching. In scenario 3, instead of blowing up the access link, let's install web cache here. I'm calling it the local web cache because we are very close to the clients. All right. Oh, and yeah, I meant local web cache here. Okay. So that you are not confused with the local cache we've talked about in conditional get, where that cache is actually very, very local on the hard disk of the user. All right. So we are only slightly local here. So this is good. So everything else stay the same. All we did is just install the machine. Now, if I ask you, changing this to 154 megabits per second versus adding a server machine, which one is more expensive? Yeah, you probably guessed, right? Labor costs, routers are expensive, cables sometimes can be expensive depending on the distance between the physical distance between the two routers. For your information, this could take millions of New Taiwan dollars. But installing a high-end server machines, it only takes this much New Taiwan dollars. So that's about 2 order of magnitude difference. Yeah. Installing web cache, so much cheaper. Great. Now, let's see if the delay is also going to be better. Or maybe if this is cheaper, then delay is going to be worse. Now, let's try to calculate this. We know the LAN utilization, and so maybe the LAN delay is also about, microseconds. But access delay, well, we'll have to know the access link utilization in order to estimate the access delay. Therefore, question mark, therefore we couldn't quite yet estimate total delay, right? But then, so this has something to do with the traffic that needs to be brought down this way, right? How many objects will be coming down this way? That seems to be the question. And if you think about it a little bit more, isn't that depend on, for all these web requests we send to the proxy server, how many of them are going to be satisfied locally? Therefore, we could just, transmit the object from the web cache through the LAN to the client without going all the way up to the servers. So that is this thing called the hit rate. Okay, amount of the proportion of the requests being satisfied locally, that's the hit rate or the success rate. Yeah, let's suppose the hit rate is 0.4. Then we see 40% of the requests will just stay here. Only 60% goes out and back. Great. So we know then the access link here, the utilization is 60% of the access link. 60% of the scenario 1. And how much is that? 60% of the traffic, then it's only this much traffic on the 1.45 megabits access link, only 58%. So we cut the utilization from 99% to 58% if we ended up having this hit rate. Now let's calculate the total delay. So 60% of the time, it's going to be long delay all the way to the server and back. 40% of the time, just on the local LAN. Now, local LAN delay, we've seen earlier, microseconds, but I'm using the milliseconds here just to take into account the traffic here. So if we go out, request object down to the web cache, and then web cache serve the local client, we have one copy down here and another copy down this way. So the LAN here, the traffic potentially could also be higher. So let's use milliseconds just to be safe and take that extra traffic into account. Now, for the 60%, we'll have to go out and back, right? So this is very negligible. This part is what? The key component. This part, 2 seconds, we know for sure. So what's remaining is just the delay here on the access link with 58% utilization. Well, how much delay is this? If there's a lot of queuing delay, we go minutes. If very, very low, only 1%, we go milliseconds. So minutes, milliseconds, well, that's, saying tens milliseconds or hundreds milliseconds, right? So I'm trying to be a bit generous here and use 10 milliseconds only. And so total delay here about 2.01. And 60% of that plus 40% of milliseconds. The dominating component is the 2 seconds. So you see here, the overall total delay on average is going to be about 1.2 something seconds. Is this better than scenario 2? It is, right? Scenario 2, you have at least 2 seconds. So what's amazing about web caching is this. The benefit is not just that it's cheaper, but the delay is also lower. And the traffic coming down this way is also lower. Hey, we did not spend any money here, and we also saved some bandwidth here as compared to scenario 1. So there's more traffic can come down this way. Isn't it nice? And that explains why we need web caching, right? It's to reduce the delay. This is also called the response time, okay? That meant the time it takes to issue the request all the way to the server and bringing down the web object. The round-trip delay of the request and response messages. It also reduces traffic, save a lot of bandwidth on the access link, and it's very cheap. Now, an extra benefit we didn't talk about is because we did not assume the uplink bandwidth of the servers being the bottleneck. If the server is poor, meaning having poor content providers out there, then, let's say that the server here is poor. It cannot afford too high bandwidth uplink. Then reducing the amount of traffic going this way also saves poor content providers some resource, some money. And so web caching there also help the poor content providers to deliver content, all right? And this could be a good thing because most of the NGOs, they might also have information to disseminate, but they couldn't provide good uplink bandwidth. And that actually gives rise also P2P file sharing. The idea of P2P file sharing is also, hey, if I have the copy of the content and another peer grab a copy of it, then this other peer can help serving the other peers. So that peer there is working pretty much like a web cache, isn't it? Like a proxy server. So you could actually think of a P2P network, a network of these proxy servers. Good. And you saw a bit already. Next slide. Coming next is going to be the second application in chapter 2. And we'll look at how FTP defines its application layer protocol. Great. So that was web caching. Quite amusing, isn't it? Good. So far, no question. Feel free to type up, but we could also talk about the questions the second break. And next is FTP. FTP, the File Transfer Protocol. This is the second application layer protocol we'll be learning here. So, see if you can identify what is the communication model, what is the structure between all these entities involved, and what is the underlying transport layer service, and what are the message types, syntax, semantics, and how are these messages exchanged. Pay attention to these. So first of all, what is the communication model? You see here, client server. Client is always the side initiating transfer, so over here, this side. And server is always the one that's far away, it's over here. All right. So what you see here is FTP is to provide transferring of files to and from the remote host. Server here is essentially allowing the users or the client access to the hard disk here. Okay, so it's a little bit like Dropbox. Okay. So a distributed file system in a way. Good. Now, file can go this way as well as this way. So you see here, it's bidirectional. Good. The protocol is defining this RFC. The number is only 3 digits. You see that this is one of the earliest internet protocols. The server there is sitting on port 21, another well-known default port number. So whenever the client needs to initiate communication, it goes to port 21, where the FTP server will be sitting on. And by the way, 21 is also the port number that Poly confuses SSH's port number on. All right, so let's take a closer look at the message exchange. All right, so FTP clients contact FTP server at port 21, this we know, and specifying TCP as the transport protocol. So FTP there uses TCP just like HTTP as the underlying transport layer service. And then the client will try to authorize itself into the server over a control connection. So what I'm depicting here is also what's going on here. The client will establish a control connection towards port 21, okay, at the remote host. So messages saying, I want to log in, here's my password, will go on this connection. After the client logs in, it's going to browse through the directories, okay, in the remote hard disk over here. So the commands changing the directories around is going to also be sent over the control connection. When the server receives a command for a file transfer, okay, so command for file transfer also travel this way as it's also a command, so it goes on the control connection. But the server now, okay, will open a TCP data connection going back this way. Okay, so that is depicted here. The data connection running on port 20. After transferring a file, the server is going to close the data connection while this one remains on. If the server needs to send another file, it would start yet another TCP connection and send the file over there. Okay. So such separation of control and data-based content on different channels, okay, in communication, we call it the out-of-band communication. If you think a little bit more in HTTP, there are two messages, right? HTTP request, HTTP response. Yeah, which one is data? Which one is control? No, in fact, each of these messages are both control and data. In HTTP request, we do have command, right? Get, post, head. But in HTTP response, we also have the status line. So these are obviously control. But in both messages, we also have the body entity. If you use a post command in HTTP request, you might be sending also some data up to the server. And very classic web response, the entity body contains the web object. So in HTTP, communication is in-band. One word, in-band, right? Data and control messages are bundled together and going on just one connection. FTP, very weird, out-of-band communication. Another thing that FTP differs from HTTP is this. HTTP being stateless, but FTP is stateful. So FTP server here actually store information about the client's previous visit, including where this client at in the directory structure before the client logged out. Okay, so next time when the client wants to log in, the server will take him directly to whichever directory the client left. So the client can continue working on, downloading files or uploading file in that space. Similarly, if you log in as a client, you might get a message from the server saying, "Oh, you logged in previously at a certain day and certain time." Okay. So this is sometimes a nice thing to do because you might want to know if there are unauthorized logging and authenticated logging, meaning someone stole your password and then use it to log into the FTP server. Next are just a few examples of the messages being exchanged between the FTP client and server. So these simple comments are messages the client sent to the server. And server typically return these return codes, right? So very much like the HTTP request, the control part sends comments and necessary information to help the command to be executed at the server side. And then the server returns certain code, phrases, and explaining of the code and the phrases. All right, let's look at the example. Oh, and by the way, again, in FTP, messages are in ASCII text, right? Data, however, on the data connection could be in bytecode, all right? So control connection there is always sending ASCII text messages. And control connection there is also allowing the server to send back status code. Okay? So these and these all on the control connection, only the data on the data connection. So let's begin. User, capital user, space, username. Hey, you guess, this must be a user trying to log in and providing the username. So this is a variable, so comment, argument. And this is gonna be sent through the control connection to the server. Server check. If the user does have an account on the server, then this is what the server sends back. 331, username, okay. And server asks, could you send me the password? So, hey, a hacker might figure out the username, but not necessarily the password. So, client here sends pass, again, capital, space, password, over to the server. And then the server can perform the rest of the authentication. So you see, capital, PASS, capital, USER, these are special words, okay? In the command messages, all right? So each followed by an argument. List, this is a special command, no argument required. What it does is to return the list of files, okay, in the remote directory. So upon receiving list at the server sends, okay, here are the files in the directory. Retrieve, RETR capital, space, file name. This is now officially to ask for a file from the server. Retrieves files. The other way around, if we want to store a file, upload the file to the server. Then store, capital, file name. Now, here are some status code and phrases the server might respond. So, 125, data connection already open, transfer starting. So this might be the server responding to a retrieve command. Okay, setting up a data connection, and then next bytes are gonna come. Or server might find that, hey, there's not enough socket to open, or there's not enough bandwidth can open data connection message might be going back. 452 error writing files. Oh, okay, so this is this case. If the client wants to put the file onto the server, and if there's not enough disk space, or if the client doesn't have the access right, the readable access right, the writable access right, then the client gets this message 452. Okay, so that's FTP. We see again, an application layer protocol defines communication model. Is it client server, P2P, or hybrid? An application layer protocol defines also what is the network structure. In both HTTP and FTP, it started off very simple, one client, one server. But you see earlier in HTTP, it kind of grows a little bit, having these proxy servers in the middle, helping with the transfer. In every one of these application layer protocols, we also need to define what are the messages to be exchanged and the order they exchange. So we see here examples of messages defined for FTP and how they're exchanged, okay, in the previous slide. Okay, through the control channel, yeah, logging messages, checking directory messages. So this is FTP. Good. I guess FTP very simplistic. So next we move on to PA4. All right, welcome back to programming assignment. This is PA4. PA4 here is designed to be a pair with PA3. So PA3 there is our file upload client, and PA4 therefore is the file upload server. Together, they will provide a file upload service. Now let's dig in. Your server there, aka pa4.go, should run like this. First, listen at the port number. So this is your port number. So check out what is the port number that's assigned to your team. And so it's going to sit there until there's an upload request from a client. It then will begin to read first the file size. Recall back, your pa3.go sends first the file size as a number in a line. And then it begins to send the file. So your pa4.go will then read one line at a time. So this is the actual file counter. For each line, you prepend the line count and then store the new line one line at a time again to this whatever.txt file. So essentially you repeat step 3 and step 4 until all the lines in the files are exhausted. And then you send a message back to the client. And it should tell the client that what is the original file size, so amount of bytes the server has received. And then the new file's file size, the amount of bytes that the server has written out to whatever.txt. You may now close the connection and terminate the program. Be a bit careful. Yeah, you do need a special port number for the assignment because it's kind of important because all of you server processes will be tested on the workstation. If you guys are sharing same port numbers, there's going to be a collision. So it's not going to work and you're going to see some messages popping up in your terminal. And sometimes it's not that easy to interpret the debug messages. So make sure that you use the port you are assigned and find out about the assignment from this PDF file, which is here again, just like what you saw in the PA3's video. So if you're team 7, the port number will be 12,007. Now, in fact, what you have learned in PA3, those very simple examples, client 101, server 101, that should be sufficient to carry you through PA4 because after all, you're implementing a server and you have seen an example, server 101 before. So that should be okay, and you feel free to move on and work on PA4. However, I'm still going to introduce another pair of client and server. All right. That should make your PA4.go's coding slightly easier. All right. What I'm introducing there is the reader object and its associated APIs, also defined in the package buff.io. That is an alternative to the scanner object that we've been using earlier. Okay. If you recall earlier when we were running client 101 and server 101, we did see that at the client side, although we're sending 13 bytes of string, but the server only received 12 bytes. That's because the scanner scan API there will ignore the new line character. Okay, so as a result, the server sees only 12 bytes and tells back to the client that it receives only 12 bytes and there's a mismatch. Now, to avoid confusion, the APIs in readers are better implemented and taking this into account. So we'll see next server 101 and client 101 being upgraded to server 102 and client 102, such that it's using the reader API. And so we don't have the confusion of exactly how many bytes we receive and how many bytes we send. And that's coming up in video part 2. This is part 2 of PA4's video walkthrough. So we'll introduce this new pair of client servers. The functionalities is identical to the first pair that we introduced in PA3. So let's start server 102.go and copy and paste the entire block here in page 2. And then start client 102.go and then copy much of page 3 into that file. You do want to replace these your port number in the main function so that it's gonna work correctly. And then start the server first. At the prompt, go run server 102.go. You'll see that it's launching the server and then waiting. Now the client code. Go run client 102.go. Send a string of 13 bytes. Great. And the server replies this time. 13 bytes received. Cool. So we don't have this mismatching problem anymore. And also, back to the server's terminal, you see hello world is printed and return to the prompt as the server program terminates. Now let's give server 102 and client 102 a try. So let me start the server on the terminal, upper right here. Go run server 101. Oh, sorry, 102. And we should see, yep, launching server. The server right there is waiting. So we can now start the client on this other terminal. And see, there we go. Client here sends a string that is 13 bytes long. Server receiving the string and printing the string on the screen. So we see hello world, sign. And server there sends back a message. 13 bytes received, and client here receiving the message is printing it out. So everything works as expected. And let's go back to the code and walk through the code. This is part 3 of the video. So let's walk through the code. Server 102. Package main, import 3 packages and the function to check for error. And the first part of the main function, which are opening of the listener socket, the data socket, and the defer closing of the sockets. Now, what 102 begins to differ from the 101 version is this. Instead of using a scanner, we're using the reader. So, connection, the data socket here, is going to be wrapped around by a reader. So we could call these nice APIs associated with the reader object. So read string here reads one character at a time until it hits this character. Oops. Let's move it back. Until it hits this character, new string. So what this says essentially is to read all the characters until the end of the line. And read string will return the entire set of characters, including the new line character, back as the first value of the call. So message here is going to contain the first line, including the new line character. Second value is always the error message. So let's just skip that. And then format printf, percentage sign S here is just going to print the message, which is an entire line. So the command prompt is going to go to the next line. All right. So the writer part is completely identical. Okay. But given that the message here contains 13 characters, including the new line. So we will see that, hey, len here will return 13, and therefore we send the message back, which says 13 bytes received. And that's why we don't have this mismatch problem running server 101 and client 101. Function, checking error, all the same. Main function, first part, again the same. Net.dial is a characteristic of a client program. Writer, which pretty much the same, right? Because we write and hello world out to the socket. And then we read a message from the connection. Now this is explained already in server 102 and print server reply. So that's it. The video walkthrough of the second pair of client-server example. Good, so we are done with PA part 1. And there was a question regarding the web cache showed up in the PA1 video. So Pei An was asking, is there an optimization process on the web cache to increase the hit rate? There is, in fact, and this needs to be implemented in the web cache for sure. Because it's definitely needed when the disk space on the web cache is used up. Okay, so then the web cache will need to decide what objects to throw away in order to keep the new ones coming in. All right. Usually, the strategy is to profile the history of these objects being accessed and use that to train the best policy. Right? So it's a training-based approach. But there could be simplistic ones like first in, first out. This might work reasonably well depending on the object access pattern. But the one that I use more for web object is this. The most recently used gets to be kept on the cache. And those that are least recently used are thrown away. Because it's very common that people see in these web object access. If someone accesses an object recently, chances much higher other people around him or her access the same object. So that is to answer Pei An's question, and let's move on to the second part of PA4. And that might take longer than
part 4 of the video walkthrough.
Than the ending time of the lecture. So feel free to leave if you have to go.
Go back to the top of the PDF file. You'll see the steps involved. All right. Keep in mind, PA4 is the file upload server, and it is supposed to work with the PA3.go, the file upload client. So once you're done with the implementation, you are ready to do the testing. Now to test PA4.go, you need a client, which is your PA3.go. So bring it over here. All right. To do the testing, you do want to make sure that the dial-up address and the port number is going to correspond to where the server is. So if the server is locally on the machine you're starting pa3.go, then hey, you just need to use 127.0.0.1, which is to indicate going to the local machine. If you're running PA4 on the workstation, its IP address is 140.112.42.161. And if you're running PA3, the client on your local machine, then you would definitely need to change the IP address of your PA3 to workstation's IP address. Now, this is assuming that the port number of PA4 is already what you have changed your PA3.go to. Why don't we walk through what I was trying to say there? So let me demonstrate. So this is running PA4 and PA3 both on Pollys MacBook. So this is local machine, same machine. Let me show you my PA4 directory. As I have already exercised client 102 and server 102, I have both files here. And I have finished implementing my pa4.go. I see also pa4.go here. I also did the bytecode compilation of my pa4.go. So you see the pa4 binary there. And I have also brought my PA3 over here and changed the IP address so that I have two versions convenient for me. One is to send the connection request to the local machine, and the other is to the workstation, okay, on NTU campus. Yeah, as you could see that I have obviously started pa4.go already, and it seems to be working, so I'm generating this whatever text file that you're supposed to generate as part of the assignment. So that's start pa4.go. Here, run pa4.go. All right, so it's launched. So over the other terminal, let's run the client process. Now, because this is on the same machine, so I will just use the 127.0.0.1 IP address version. And by the way, you're seeing 11,999 here. That's because Pollys PA4 is running on this port number, so that I will not be conflicting with all you guys' port number. Let's see. What's wrong here? Oh, yeah, I forgot about the suffix. There we go. Yeah, let's send client 101.go. How about that? Client 102.go. Let's see. All right, so client here sends, it has already sent the file of 527 bytes, and it receives a message back from the server saying that the server receives exactly 527 bytes, and the server there generates another file that's 605 bytes. Note that the output file is 605 bytes because on the server you are asked to do what? Prepend the line count before each line. So the extra 605 subtracting 527 will be the extra bytes for the line counts. Good. So yeah, the numbers are consistent. We seem to be okay. Next is that you want to upload your pa4.go to the workstation and do the testing there as well, just to make sure that Poly will see that your pa4.go will be running okay on the workstation. Let's log in there. SSH. And let me pretend that I'm one of you guys. Let's make it team 15. Well, yeah, because I know the name of the station is nslab1.e.ntu.edu.tw. That is slightly easier to memorize, so sometimes I forget. Yeah, I told you guys that the IP address is this, and I encourage you to use the IP address. So SSH username at the IP address of the workstation. Let's see. Yep. Here. Now trying to log in. Great. So I'm in. I'm on the workstation and the home directory of user CN team 15. Let's see what's in here. Yeah, a bunch of directories, I guess. Yeah. Very much like you guys' home directory. Good. Now, let's create PA4, a subdirectory. Oh, sorry, not that. Make directory PA4. That creates a subdirectory. You should see PA4 showing up. Right? Let's go there. CD, changing the directory to PA4. There should be nothing here. Yep. And so we need to upload pa4.go over here. I'm just gonna do it in a fancier way. You guys feel free to use FileZilla and do the FTP to upload the pa4.go to the workstation. Let me just show you. If you use the terminal and if your machine has the S copy, secure copy, activated or installed, then you could do the same. So that I can save the effort to start FileZilla. So let's copy pa4.go over to, again, sorry, username at the machine. And we also need to specify the directory we want the file to go to. So tilde. This is the home directory of CN Team 1, and because we just created the PA4 subdirectory, let's copy pa4.go to our account's PA4 subdirectory. Oh, sorry. There's a typo here. I should not be getting this message. This is going to the other machine, so let's cancel that and change the IP address. There we go. Great. Let's hope. There. File, secure copy completed. And let's see. Yep, pa4.go is right here. So we could now execute pa4, your file upload server here. Great. Service launched. And I'll have to run this version here if I'm doing the client on my local machine. So I should be using this guy here because the IP, the dial-up IP address is the workstation's IP address. Great. That's upload server 102 this time. Let's see. Great. So client says 572 bytes uploaded. So server 102 is longer than the client 102. And it receives, the server says it received 572 bytes and a file of 656 bytes generated. Complete match. Great. So that completes the testing for your pa4.go.
If the previous video is not quite sufficient to make sure your pa4.go is doing the right thing, you can try this alternatively. Download Polly's pa4.go's bytecode. So Polly has already finished her pa4 and compiled it into a bytecode. And it's available over here at this URL. You need to log into the workstation and download that file to your account. And that can be done by doing curl again, but this time you'll be downloading the pa4 bytecode. Let me copy this line so that it's easier for me just pasting the terminal when we're doing demonstration. So make sure that you push it to a separate file. Let's call it the Polly's pa4 for now. Good. Now, after you do that curl, you will see a new file being added to your directory. You can't quite just execute it yet. Another thing you need to do is to change the permission. So chmod here allows you to change the permission of the file. And what you need to change is to add executable write to the user, which is you. And once you've done that, pollys pa4 is not an executable file. Therefore, you could call and directly execute it. This paragraph is just to explain again, pollys pa4 bytecode there is going to sit on port 11,999 so that it does not conflict with you guys' server running also on the workstation. Good, so let's move to the demo mode. And let me just walk you through how to do the curling and changing the permission. So let me paste that line, great. And make sure that you set it go to pollys pa4 here. Otherwise, it's going to display the bytecode on your screen. It's going to take a while and it's going to be messy. So direct it to a file. Okay, now you could use a different file name. Now we've seen pa2-pa poly2 no sorry I actually want it to be pollys pa4 pollys pa4. There we go. And that should create this file here. But again, you see here the user's permissions accessing the file does not have the executable right. So if you just simply try to execute it like this, no, you're gonna get this message from the operating system, permission denied. So make sure you do change mode user, adding the writable permission, and then pollys pa for the file name. That should give us the permission to execute, and there we go. Launching the server. Now, testing again. So, I'm doing the client on my local machine, and the server is on the workstation. So, I'll have to go run pa3. This version. .go. Is it working? Yeah, it's taking a bit time. There we go. So that's upload server 102.go. And there we go. File size is 572. And the whatever text file should be 656. Let's see if the whatever text is created. Sorry about that. Yeah, it is created and the size is 656. If we show the content, you see, server 102. This is the coding server 102. Launching server. And for each line, you see, right there. The line count is prepended to the line all the way till the end. And there are 31 lines in server 102.go. Alright, so that's the walkthrough for doing the bytecode download and testing. Let's go to the browser again and finish the rest of the testing. Alright. Now, occasionally, but chance is very low. Okay, chance is very low that 2 or more teams might be simultaneously trying to run pollys bytecode. In that case, you will still have the conflict, sorry. Because PA4 is always running on 11,999 if both of you trying to execute PA4. Whichever executed first will be occupying 11,999. The other team that is slightly late then will have the port conflict problem. So there are 2 ways to resolve the issue. First, the late team there, give it a bit time because once the previous team finished testing, then the port 11,999 will be released. Okay, so solution number 2. chance is also very high the process that's running on 1199 is some other team starting PA4. So why don't you just go ahead and try and by starting your PA3 Go. That should also work, and you should see PA4 working. But I'm not quite sure if the result, whatever the server is writing out, is going to show on your screen though. Okay, so yep, that's about testing. And this is the end of video number 5. This is the last part of the PA4 video walkthrough. Good. Go has a significant documentation project there. So if you go to this link here, you will see all the APIs available if you include the buff.io package. In buff.io package, you see that reader, scanner, and writer. These 3 major objects provide really nice APIs for you to access IOs, and it allows you to access a wide range of IOs. Really nice. And in the pair of client server here in PA4, you see that the reader object, the API there is significantly richer also than the scanner. So one can read byte, one can read a number of bytes, one can also read a line, read a string, and or just simply read. Okay. And by the way, read is the most basic API for any system IOs. So if you're creating a network socket without the buff IO, you can also just call read to read from the socket. But the thing is that that is the only API that you can do. Okay, so unlike in readers, you can read flexibly right there online. Okay. And by going over buff.io, you see, because buff.io package is entirely the community's effort. Okay. So read there is native system IO. So you see that the extension is so powerful that makes it so much easier to implement. And this is also why the developers these days appreciate Go. So it has a very rich set of APIs that are coder friendly. Okay. Now with this addition, the future generations of coders would also benefit and therefore develop additional packages to make it even better. This is what most of the coders know about the power of open source. All right. Hopefully you get to experience more about sharing code with other people and taking free codes from other people, and then in return also feedback by contributing code. So last is just to submit your PA4, which is very much in a routine, just like how you submit PA3 and PA2. So I'm just going to skip talking about this part. And that's the end of PA4. Enjoy. All right, good. So you are completely free to go. And Poly does hold office hour, and because if it's a issue with your programming assignment, it might be easier to do it face-to-face. So you try the code and let me see what is the debugging message popping up, and that might help me address the questions you have. So I'm going to be in my office. I'm going to let the stream goes on for another 5 or 10 minutes. If you have further questions to ask, feel free to type in. Yeah, that's all. Good. By the way, I'm also going to start eating my lunch. Yeah, so if you don't mind seeing me eating.
Oh, hi.
Hello.
Hi. Oh, you're fast.
Yeah. Do you have
Alright.
a second or?
Sure.
Yeah.
Uh-huh. So it would be easier if you show me what was wrong.
Yeah, I was working on PA3 for like a few days now.
A few days. Wow.
Yeah. And like the program, like it starts, it works, but then yeah, I will show you. Um, show you oh yeah, that's the one when I run it
Uh-huh.
and I can
And then
put
you
in the
hang.
input
Right.
and then like nothing happens.
Mhm.
Wait, Control Q to stop, right? Control C.
Are you still connected? I can
Yeah.
tell you. Okay. 161 and 12,000. That seems to be.
Yeah. Oh, it's probably because.
No, you're in into you, so you should be able to log in. If it's not responding, that's odd.
Maybe that's the problem.
Maybe
why
the
my
server.
program doesn't work as
Maybe
well.
the server is not up.
Because the same thing happened when I wanted to run my program.
Mm-hmm. Oh, it's not accepting connection, in fact.
Maybe that's why.
Could not resolve. Oh, alright. Oh, okay, sorry. Typo, sorry. Oh, it's working for me.
Yeah? Okay, I will try again.